Assalamualaikum. Welcome back to the part 2 of the final exam revision. Okay, so we are discussing on the final exam 23-24, semester 1, Q3 and Q4. Okay, so we go to the questions, which is this one, where you are given RLC network in figure Q3A, where the resistance value is 1 ohm, the inductance value is 2 Henry and 1 Henry, and the capacitance is 0.5 farad. So you're required to find the transfer function EC over ES. Okay, so this is your EC and the capacitance, and the input is voltage supply is ES. So as usual, you just replaced all the values of the circuits. Okay, uh, where you have R1, L1, capacitance, resistance, inductance. Okay, and you have I1 current over there, I2 current over there, and resistance is 1 ohm. This one is 2 Henry. This one is your EC. This one is your E. And R2 is 1 ohm. L2 is 1 Henry. And finally, the capacitance is 0.5 farad. Okay. So our target is to find the transfer function, which is EC over E. Okay. Where EC is the output voltage drop at the capacitance, and E is the voltage supply. So we have two loop here, which is loop 1 and loop 2. Okay. So we wrote the equations, okay, for the equations, which is loop 1. Okay. Go to R. R is 1. Okay. Henry, which is plus 2S. Then plus 1 over CS, which is for the capacitance. Okay. So this one will be I1, and this one will be I1 minus I2. Okay. Then for loop 2 is where ECS is equal to 1 I2. Okay, don't forget this one is I1. ECS, okay, which is 1 I2 plus 1 Henry 1 I2. Okay, for the inductance. And of course, this one will equal to the 1 over 0.5 S I1 minus I2. So we rearrange all the equations so that it become 1 plus 2S plus 2 over S I1S, okay, minus 2 over S I2S equal to for supply equation loop 1. Then this one, the second loop will be 2 over S plus, this one is bracket, I2S equal to 0. Okay, so this one is loop 1, and this one is both equations are in matrix form. Okay, 1 plus 2S over 2 over S minus 2 over S. Okay, so we want to solve for I2 because we want to get the current flow, okay, at the EC. So I2S is equal to modulus minus 2 over S over delta. Okay, so delta is the matrices, the determinant of the so that is delta and can be simplified as delta 7 plus 3S S squared simplified divided by S. Okay, and then I to S divided by E over S is equal to 2S divided by delta. So it will become 4 and ECS is equal to VR2 BL2, which is I2. So this I2S will be rewrite as S plus 1. Okay, so you use this I2, insert inside the I2S ES. Okay, so it will be ECS, okay, over ES, which is 2S plus 1, 2S cubic plus 3S squared plus 7S plus 4. Okay. If a capacitor is at a series in between the resistor R1 and inductor N1, okay, meaning that we add a capacitor, okay, determine the new transfer function. So in that case, C2 5 farad added in series between R1 and L1. So find the new transfer function, which is I2 over ES. Okay. So what will happen is you just add capacitance in the equations, okay, which is 1 over 2S plus 4 over S. Okay, this 4 over S due to the 0.5 farad minus 2 over S minus 2 over S and 1 plus S plus 2 over S, which is the existing capacitance. Okay. Then simplified, 1 plus 2S plus 4 over S minus 2 over S divided by delta. Okay, and delta is the determinant, okay, of 1 plus 2 over S. Which will give you 9 plus 3S plus 2S squared 6 over s plus 4 over square. Okay, so insert all the values that you derive. And simplify it. You will get 2s cubic plus 4s plus 3s cubic. Okay. So the next question is question 3b, which is the mechanical system shown over here. Okay. So the input is external force applied to mass M2. So we have variables x1 and x2 as the displacement, okay, motion towards the right, respectively, and assume all initial conditions are equal to 0, and damper, which is FV1 equal to FV2 equal to FV3. Okay, sketch the body diagram and solve the differential equations. Okay. So we draw the free body diagram. For M1 and M2. Okay. So when we draw free body diagram for M1, M2 is standstill. If you draw free body diagram for M2, M1 will be standstill. Okay. Free body diagram for M1. So this is your M1. Okay. The input is applied to the mass M2. So in M1, there is no input force. Okay. So what I will do is I do like this. Okay. M1, X1, double dot. Okay. For the free body diagram. X1, X2, X3. FV1, X1 dot. FV2, X1 dot. FV3, X1 dot. Okay. That is the frictions. And then the spring, K2, X1. Okay. And then on the right hand side is the FV1, FV2, FV3, X2 dot, and then K2, X2. Okay. So from here, you can write the differential equation from FBD M1 which is given as M1 x1 double dot plus FV1 FV2 FV3 x1 dot plus K2 x1 equal. Okay, sorry, not equal. Continue. Okay, minus x2 dot and minus x2 equal to 0. So this is equation, differential equation for from the free body diagram M1. Untuk continue free body diagram M2. Okay, so for free body diagram M2, the force is over here. Okay, force is over there. Then M2 have their own force. Dot at V1 x2 dot at V3. Okay, plus K1 and another one, K2. So on the right hand side will be FV1, FV2, FV3, okay, x1 dot, x2 dot, x3 dot, okay, dx dt plus K2, x1. Okay, so you have 1, 2, 3, 6 on the left hand side and 5 on the right hand side. So is it 5? 1, 2, 3, 4, yes, 5. So the differential equation from free body diagram M2 will be M2 x2 double dot plus FV1 FV2 FV3 x2 dot, okay, plus K1 K2 x2 minus FV1 FV2 FV3 x1 dot minus K2 x1 go to the input force. Okay, so use the Laplace transform. Okay, to identify the transfer function. X1 over S. Okay, X1 is the output, F is the input. Plus 3 plus Q2 minus Q2 equal to 0. So FV1, FV2, and FV3 is the same. So we just use FV1, okay, as the representative. Then the second equation will be x to s on the second body diagram minus fx. Okay, so this one will be FBB. This one is FBB. Then we plug in to the matrices file. M1 S square plus 3 FV1S plus Q2 minus 3 FV1S plus Q2. Okay. Minus 3 FV1S plus Q2. This one will be N2 S square plus 3 FV1S plus P1 Q2. Okay. All this will be multiplied by x1, x2 equal to 0. I'm sorry because the space is not enough due to my handwriting. Okay, so all this multiplied to the x1, x2 equal to 0f. Then you simplify. Okay. You simplify x1 over fs equal to 0 and minus m2 okay, divided by delta. So delta is the determinant of the main equations. Okay, so it's quite long, so I put it here so that you can compare with your derivations. Okay, S to be. 3 Q1S plus Q1 Q2. Okay, so when you simplify everything, so you will get X1 over F S is equal to 3 F V1S plus Q2. Okay. Question C, which is still under Q3, is the electromechanical system. Okay, where you are given the open loop transfer functions here. Okay, then you have to insert all the values of the parameters K1, RA, GM, and everything, so that you will get a transfer function in the S form. So let me show you. Okay, how to solve it. Go to the show me. Okay, the new one, because maximum is 50 pages. Okay. So for Q3C, okay, we have part 1, which is the torque, okay, is minus 15 omega m plus 600. Okay, where F omega m is equal to 0, EM is equal to T stall, it's not moving, at 600. That is from the graph. Okay, 4. This is 4 omega m. Second one is for Tm equal to 0, 15 omega m is equal to 600. So omega m is equal to omega root at 40 radian per second. Okay, so that's why the total inertia, okay, is equal to Jm, Ja N1 over N2 square. 2.75 for JM, initial for JM. Total damping dE plus dL load, which is dN is equal to 5.5. Electrical constant, which is KT over RA equal to T star over A, 600 over 50, which is equals to 12. So that's why KB is equal to EA over omega no load 50 over 40 1.25. Then after you get all these parameters value, so the transfer function, okay, will be theta m over EA. So you insert all the values there. So you will get 4.36 S plus 7.45. Okay, where theta m over theta L, motor and load, N2 over N1, divided by 500, you will get 20. Theta m 20 over theta L. That's why theta L over EA over 20 7.45. So this is the final transfer function. Second question is to determine the mathematical expression for the rotational systems. Okay. So part one is the electromechanical system with the gears, but part two is for the rotational system. Okay. Where you are given theta L, the angular rotation of the load. Input voltage is EA, flow volt. Okay. Degree of rotation at the load is 5 seconds. For theta L, to the 10, 0.218 from the previous derivations. Okay, so theta L is equal to 10 over S, 10 volt. Okay, input. So when you take Laplace, it's 10 over S. So theta L, you will get 2.18 square S plus 7.45. So how to solve this? Okay, so you have to use a partial fraction expansion. Okay, so theta L, A over S, B over S square, 7.45. Okay, so solve it when S is equal to 0, 0.293, and S is equal to minus 7.45. C will be 0.0392. So use B, C, solve A, so you will get A 2.18. Okay, so therefore theta L is equal to 0.392 plus square theta L theta LT inverse Laplace plus 0.293 plus 0.0392 exponent, okay, at 5 seconds at time t is equal to 5 seconds. So theta L is equal to 1.073 per second based on the uh, theta L t expressions just now. So we finish question 3. Okay. So now we move to question number 4. Which is this one. This one is under state space modeling. Okay. As usual, we have two loop of RLC equations. Okay. The input voltage is VI, and the output voltage is R2. So this is your output, R2. Identify the state space representation. This is the state space representation, still remember. The state variables are 3 state variables due to 3 active elements, L1, L2, and pistons. Okay. So in this case, X1, I, R1, X2, BC, X3, I, R2. So the value of resistance is 2 ohm over here. R2 is 3 ohm over here. Inductor is 0.5 Henry. L2 is 1 Henry. And capacitance 0.25. Okay. Right. So we start to derive. Question 4. R as the state space model. Okay. So we insert the value 0.25. R1 2 ohm. Inductance, so this one is 3 ohm, 0.5 Henry, 1 Henry, and the power supply. Okay, is the input and output. State variables defined as so. Want to find the derivative state variables. Okay, which is a dir1 dt, dvc dt, and dir2 dt. Okay, so we start to derive the equations. Okay, so we have two loops here. Loop 1, loop 2. Okay? Start with loop 2. L2, VR2 is equal to VC. So VL2, VC, VR2. Okay. And VL2 is L2 DIL2 dt. Okay. Equal to VC minus IR2 R2. Okay. That is the current through the loop 2. Okay. Then we manipulate these equations. IL2 is equal to IL2 1 over L2 VC R2 over L2 IL2. Then we go to the loop 1. Loop 1 equation is minus VI plus VL1 plus VC equal to 0. VL1 is equal to minus IR1 R1 minus VC plus VI, the input. Okay, so this one is L1 DIL1 dt is equal to minus IR1 minus VC plus vi, and IL1 is equal to IR1, okay, is equal to R1 over L1, IR1 minus 1 over L VC plus 1 over L1 VI, okay. And if you look here at the circuits, there is a node there, okay. So Kirchhoff current law at the node, okay. IL1, IL2 is equal to IC. So IC is C D V C dt, which is IR1, IR2, okay. So that's why dVC dt 1 over C IR1 plus 1 over C IR2. Okay. And the output is V naught VR2. Okay. So that's why equal to IR2 R2 output. So now you have the output KCL, loop 1 and loop 2. Okay. And then from there, you plug in into the matrices. Okay. These equations, these equations, these equations, and these equations. Okay. So what I will do is okay. Then the matrix A, you see, R1 over L1, 1 over L1, 1 over C, 0, 1 over C, 0, 1 over L2, R2, 1 over L2. Don't forget to insert RLC values. Okay. So what you will get is -4, -2, 0, 4, 0, 4, 0, 1, -3, x1, x2, x3. Okay. Plus 2, 0, 0, 9. This is the state equation, and the output equation will be not Okay. 0, 0, 3. Okay. The final state space model. Question 4b is the rotational mechanical system. Okay, is given by this, right? So we have to determine the state space representations. Okay. Question for the rotational mechanical system. Sketch the free body diagram and then determine the state space representation. So for this system, it's similar to the mechanical translational system. Okay, so add theta 1t. Okay, so J1 is equal to theta 1 double dot plus the damper D2 theta 1 dot plus K1 K2 theta 1 minus K2 theta 2 minus D1 theta 2 dot equal to 0. This is equation number 1 for initial J1. For initial J2 at theta 2, J2 theta 2 double dot plus D1 plus D2 theta 2 dot plus K2 theta 2 minus D1 theta 1 dot minus K2 theta 1 minus the torque T, okay, equal to 0. So from here, we can simplify it become theta 1 dot equal to minus d1 plus d2 over g1 theta 1 dot minus k1 k2 j1 theta 1 plus d1 j1 theta 2 dot plus k2 j1 theta 2. And for the second one, we can simplify as theta 2 double dot d1 j2 theta 1 dot k2 j2 theta 1 minus d1 plus d3 j2 theta 2 dot minus k2 j2 theta 2 and the input. Okay, so this equation will be uh, crucial for the state space modeling. Okay, because when we look at the state variables, okay, which is x1, x2, x3, and x4, theta 1 dot, this is x2 dot, theta 1, x4. Okay, so you replace all this inside equation previously, okay, which is theta 1 and theta dot. Insert all above in theta 1 double dot and theta 2 double dot. Okay, so what we will get is something like this. Okay, the input T and the output will be theta 2 dot T 0, 0, 1, 0. Okay, and this one is from the equation of theta 1 and theta 2 dot. Okay, straight away put inside. Then question, the last one is question 4C, is the block diagram reduction. Okay, looks straightforward. Okay, we look at the questions. Okay, this one. Okay, so you just simplify this one. This one is the feedback. Okay, negative. Uh, this one is feedback, positive. This one is feedback, positive. And this one is feedback, negative. Okay. I'll show you for this one. Simplify this one. So it will be G2 1 plus G2 H1. Okay. For the positive feedback, this one, it will be G7 1 minus G7 H3. Okay. One positive, one negative. And then this one will be cascaded to G1. This one will be cascaded to G4. So cascaded, meaning that you multiply everything. Same to the bottom one. Okay. So the final answer of this will be C over R, G1, G2, G3, G4, 1 plus G2, H1, 1 minus G3, H2, plus G5, G6, G7, G8, 1 minus G7, H3, and 1 plus G8, H4. Okay. So that's all for our discussion today. Thank you very much. Okay, for your attention. Uh, Try our best, inshallah. Put an effort to derive and to solve all this problem. Thank you very much.